Good morning, everyone. Time for the next WOSMIP remote. Our next speaker will be Derek Haas from the University of Texas, who will talk about emissions from molten salt reactors. Derek, over to you.
Thank you, Ted. And thanks for the invitation to join WOSMIP once again. So this is going to be a follow-up to a presentation that Steve Bogalski presented for me back in 2016, I believe. I wasn't able to attend, and so we just wanted to give an update on what we've been looking at. So we're looking at radioxenon emissions estimates for molten salt reactors. This work was done by a master's student, Joe Kowalczyk, and I was his supervisor. So jumping right in, we're looking primarily at what emissions might look like for Generation 4 reactor designs. We're pretty familiar with most of the Generation 3 and Generation 3 Plus designs, so we just want to look at what potential new emission sources might be. In the previous presentation, I talked about several different designs and evaluating what each one might pose a potential emission scenario from qualitatively with just a little bit of calculations thrown in there. We really focused on the molten salt reactor because of the liquid fuel aspect and the fact that the radioxenon would be released potentially with significantly higher rates since the fuel is not sealed into a solid form. So just zooming in on that molten salt reactor design, the main thing here is that when you have a liquid salt fuel, the uranium atoms are suspended in the salt and any fission products can be released whenever they go through this chemical processing step as part of the loop the fuel takes throughout the reactor. So the calculations that we did just assumed all the radioxenon came to equilibrium, and what would that release look like? This is a very quick estimation. We just wanted to see what the scope of the problem might be. That gives us at equilibrium for xenon-133, something like 2 × 10⁻XVI becquerels per day per 100 megawatts of reactor. And that is a huge number. But note that that is what's in the fuel. Emissions could be some small fraction of that. So this is what we were doing here, was to try to figure out with a more realistic scenario, what do those emissions look like? In order to base it on something that had actually been done before, we started with the molten salt research experiment at Oak Ridge National Lab. This was a reactor that was built and operated in the 1960s as part of a Department of Energy project looking at this reactor design. It had a max power of 10 megawatt thermal, but it was only operated at lower powers most of the time with an average power around 5 megawatts. And the radioxenon release limits that they gave themselves were about 2.5 × 10⁻XIV becquerels per day. So still a significant emissions level, but lower than that 10⁻XVI, 10⁻XV we saw in the previous calculation. And this is an image of the reactor itself. So you have the reactor core where it goes critical and multiple flow loops where the salt moves around. In point number 3, you have the fuel pump, and this is actually where many of the gaseous fission products are removed. It's important in this reactor design to remove those gaseous fission products because xenon-135 has such a high neutron cross-section. So you can be more efficient with your neutrons if you remove that xenon. That means that it is definitely a waste product that needs to be taken care of. So when we set up our origin models, we did use origin 2. And we had 2 main goals here. One was to confirm Bell's calculations from 1970. These were calculations done by the scientists that were working on the project using origin. And once we had that, we thought we could develop a starting point to evaluate other abatement systems that were different than the one used in the MSRE. So we have the inputs to that model here. It's basically the reactor has the gas removal system from the salt. The gas goes into an abatement system that is an activated charcoal bed, and then the charcoal bed delays the xenon to let it decay before releasing it out the stack. And the values we have from those technical documents from the MSRE is that 38% of the noble gases were removed per cycle of the fuel through the gas removal process. There was approximately a 90-day holdup in the activated charcoal bed, and then the flow rate of air going through the stack was 7 cubic meters per second. And that was diluting the xenon as it made its way up the stack. So while these numbers are good starting points, they are, The data is limited from this experiment, and so we just wanted to see how we compared to those early models. One of my big questions going forward is going to be, how accurate is this 90-day holdup? Is all of the gas experiencing at least 90 days, or is it a wide plume of xenon moving through that charcoal bed? So that'll be one thing that we need to figure out in the future. And once we get this to work, we are going to be able to change these inputs and figure out how different abatement systems might work. So let's jump straight to the results. This is the activity in becquerels per day of the different isotopes. So we have xenon 131M, xenon 133M, 133, and 135, and then an all gas value for one of the scenarios. Along the x-axis, we have several scenarios looking at a calculation from 1965, a measurement of the MSRE from published in 1973, the origin model that we are comparing to from 1970, and then these two values here, the origin 2 models, are the work that we did. Last, we have the Nuclear Regulatory Commission limits on emissions from the 2019 regulations. So what we can see here is that our model with the exact same inputs show almost exactly the same release values as the 1970. That's a good check. We're happy with that. We do note that those values are just above the recommended release limit values per day from the recommendation that came out of WOSMIP years ago of 5 × 10⁹ becquerels per day. So that's immediately for a 5 megawatt thermal reactor. The MSRE would have been exceeding those limits with the abatement system that it had, assuming these are correct. So this is for continuous removal of the xenon and pushing that xenon out the stack. Another value we have is what we call origin 2 without stripping. So if you're running the reactor, but you're not removing the noble gas from the reactor, you can build up to closer to equilibrium values, and that's when you could have a sporadic release of 10⁻³ becquerels per day. And this would be similar to you're running the reactor, the gas is sealed in there, and then you shut down and crack open the reactor for refueling or something like that, or to change out parts. You could get these larger releases that are closer to the equilibrium value. The next thing we see is that existing regulations in the US are not going to drive the mitigation where they sit now. So all of these values are below that for a 5 megawatt system. So if a commercial system were brought online with a few 100 megawatts, we're still not looking at bumping up against the regulations with the MSRE abatement systems. There is some encouraging experimental data. This measured value published in 1973 of the activity of all gases coming out the stack, we're not sure how reliable that data point is, and so that will lead to one of our other conclusions later on. But one question we have is, might the noble gas removal rate been higher than the 38% that was used in the Bell calculations for the MSRE? If your noble gas removal rate is higher than that 38%, you keep the levels in the reactor lower, and so then you could have potentially a lower release value. There is some point at which this should level off, but we haven't done the calculations to find out what those values are yet. So our conclusions from this initial effort is that continuous efficient noble gas removal from fuel in a molten salt reactor can significantly reduce the emission values. We also find that a sealed molten salt system will be a source of large sporadic releases of radioxenon when the reactor fuel lines are disconnected. And probably most importantly, we need more modeling and new experiments to guide reactor subsystem designs to minimize emissions from future molten salt reactors. So we have some promising developments along these lines. This is a 2018 DOE report looking at what a noble gas or an emissions abatement system might look like. And included in this are both the activated charcoal bed that was used on the MSRE, as well as a new component here looking at either pressure swing or cryogenic distillation to remove and store excavation products. That's valuable from a standpoint of reducing radioxenon emissions, but it's also valuable to the reactor itself, because this also allows you to bring the helium cover gas that's used back into the reactor so that you're not just having a once-through cycle of your helium. You get significantly more helium efficiency in the reactor operations. So I'll call this a promising development, and hopefully these types of things stay in the reactor designs going forward. So with that, I'd like to thank Professor Kevin Clarno here at UT Austin. He had some insights into modeling the MSRE, and thanks again to the WOSMIP crew for asking me to join.
Thank you, Derek. It's I will say, a frightening prospect that molten salt reactors may be releasing even 10 to the 14th becquerels per day. That's a very high number. I guess that's dependent on the size of the reactor, of course, but still, even at 10 to the 14th becquerels, it's going to be a dominant source when and if they start operating. So it looks like we have one question from John Burnett. John?
Thank you, Derek. That was an excellent presentation. I have a question. How does the radioxenon isotopic fingerprint compare to other types of conventional reactors, such as the PWR or AGR, for example?
So as long as the xenon abatement systems are working as planned, it's dominated by the xenon 131M and the xenon 133. Working outside of planned, we really don't know at this point. So we'll need to do either measurements against systems as they come online or more modeling in the meantime.
Thank you.
Thanks again, Derek. If we don't have any more questions, then we hope to see you engaging at WOSMIP. Your contributions have been valuable. I know you noted this several years ago in one of our meetings, so more information on that would be great to see. If you all have questions out there and would like to get them to Derek, I'm sure he'd be happy to answer those, or you can send them to us and we can relay them to him. Thanks again, Derek, and be safe, everybody, and we'll talk to you later.